Hello there, welcome to this video. In a previous video, we derived the identities that allowed us to convert from a coordinate system that is Cartesian into a polar coordinate system in 2 dimensions. In this video, I'll show you a few examples on how you can use those identities. Let's begin with an example. This example, we have a Cartesian function and we want to convert it into polar coordinate function. So to do this, we know how to convert x into polar coordinates and y into polar coordinates. I'm literally just going to sub in the identities for this. We learned before that x is our cos theta, y is our sine theta. And now we just simplify. R squared cos squared plus r squared sine squared 3/2. I'm just going to put r squared because it's common to both of them. So then we're left with cos squared plus sine squared. I haven't written theta, but it should be thetas. All to the power 3/2. Now we know that cos squared plus sine squared is 1 from our trig identities, so this just becomes r squared to the power 3/2, which, when we simplify, becomes r cubed. We can do this another way by using the inverse identity, and in this case it does make it quicker actually. It's not always the case, but in this case it is. Now the inverse states that x squared plus y squared is r squared. So in Cartesian coordinates, immediately you can see it just becomes r cubed. Let's try an example where we then integrate over the area. So we'll do example 2. In this example, we have a function in Cartesian, which is just x, y, and we have a region, x squared plus y squared is smaller than or equal to 1, x is greater or equal to 0, and y is greater or equal to 0. The first thing I'm going to do is I'm going to convert the Cartesian function into a polar coordinate function. So the function in polar coordinates, we know that x is our cos theta and y is our sine theta. So times them together, it becomes r squared cos theta sine theta. Now we've converted the function, we also need to convert the regions because you can't convert one without the other. For this, I'm going to sub in the identities. X squared plus y squared is r squared. Therefore, r squared is smaller or greater than 1. Then when we square root this, square root of 1 is 1. We have the first region. X is greater or equal to 0 and y is greater or equal to 0. X is r cos theta. And r sine theta for y is greater or equal to 0. For the r cos theta, to make it equal to 0, either we have r is 0 or pi over 2. And exactly the same for r sine theta. To get it greater or equal to 0, well, it's equal to 0 if r is 0 and to get sine theta equal to 0, theta is 0. So from this, we can calculate our new region. We know that r has to be 0, or r is greater or equal to 1. So the new region, 0, r is between 0 and 1, and theta is between 0 and pi over 2. Now we've got everything we need to then do the integral. So let's do the integral. Zero and 1 for r, 0 and pi over 2 for theta, and the function is r squared cos theta sine theta. And remember, when we're doing an area, it's r dr d theta. So 0 and 1, r cubed, because we've got that extra r there, dr, and between 0 and pi over 2, we can do the first one straight away. This just becomes r to the 4th over 4 between 0 and 1. How are we going to do cos theta sine theta? I am going to use a change of variables, and I am going to make sine theta equal to u. Therefore, du by d theta is cos theta, so d theta is equal to du over cos theta. Sub that in. I'm going to leave the limits because I'm going to convert it back later on, so I don't need to convert the limits. Sine theta is u. We've still got the cos theta there. D theta is du over cos theta. The cos's cancel. Left with u du, which is nice to do. So it becomes u squared over 2. And then if we sub it back in, sub u back in, we end up with sine squared theta over 2 between 0 and pi over 2. And this one was r, 4 over 4 between 0 and 1. Therefore, this one, quite nice, just becomes 1 over 4. Sine squared theta to the pi over 2 just becomes a half. And then we're left with an answer of an eighth.